Hello again and welcome. Somebody had left a comment about using connector protectors on the end of the NanoVNA. Basically you have a male connector on the one side and a female on the other, and then you could attach this to your Nano. So a couple of things I'd like to mention about that. First of all, the Nano being a $50 unit, I really wasn't too concerned about damaging the connectors. Another thing, you notice that it still has these blue cables that I've used for all my testing attached. Even on my HP network analyzer, I'm not in the habit of taking these cables on and off. I typically just set the thing up and I leave it, and you can see that's what I've done with the Nano. The wear and tear on these cables is actually going to be the end here. So if I was going to add a protector, it'd be to the back side of this. You know, so if you wanted to add a couple of these to your Nano, would it cause a problem? I kind of doubt it. The Nano isn't going to really be sensitive enough to probably pick that up. So you're probably okay adding them if you feel more comfortable in doing so. You know, I'm not going to do it. Another thing that I saw, somebody had asked me about using the torque wrench with this. Now again, that's something I would just do out of normal practice. And again, this is just a click type. You just want to make sure that you're holding it perpendicular to the connector. It's just a one click. We just loosen it, draw it up till it clicks, and you're done. Somebody had asked about the torque rating for this wrench. This particular one is at 8 inch-pounds. You may want to check yours with a fish scale or something. Just make sure that it's reasonably close. Am I concerned about snapping these off the circuit board? Probably not. I mean, I've used these end-launch connectors on quite a few projects, and you can see it basically wraps around the circuit board. You know, if you're shearing off the tangs on these things, I've got to believe the connector itself was probably flawed, or the wrench itself is probably not calibrated. Personally, I've never seen anybody damage a connector by using a torque wrench, except for that one time that I mentioned where the person had never used a torque wrench before and they're holding it off to the side like this instead of using it perpendicular to the connector. As long as you're not doing that and your torque wrench is calibrated, and assuming that the connectors are good, it shouldn't be an issue. So another question that came up is somebody was asking about the cable lengths and if that makes a difference. And one of the things they had asked is basically, could you get rid of one of the cables? I'm not really sure what they were doing, if they were applying just the SOL standards to channel 0 and then for the through they jumped it across, or if they had the cable installed on channel 0 and maybe they were using the through cable here and then installing standards on the back side of that. But regardless, it really doesn't matter the length of the cables. You could literally run this thing with a single cable if you wanted to. I don't think it's going to cause a lot of problems. I probably wouldn't take these standards, for example, that they've supplied with the Nano and start attaching these directly to the connectors like this. Again, these things are rigid compared to something like this where the center conductor is allowed to stay in place while the nut turns freely. That's not what happens with this. As you rotate this, you are turning the center conductor, which is definitely going to wear on that center pin. So personally, I would just use this thing with the cables that are supplied with it. But does it matter as far as the length? No, it really isn't going to matter. And the reason is because this is not really a full 2-port instrument. So again, this analyzer can only source power off of channel 0. So again, you can measure the magnitude and phase of the reflected power, or S11 off of channel 0, or you can measure the through power, and that would be on channel 1, and that's S21. The thing you can't do is measure like S22, and you can't measure S12 with this. I've seen people talk about having the cables connected to their DUT, and then essentially what they do is they'll flip the cables. You could certainly do that, but you're disturbing the setup. At 900 megahertz, is that going to make a difference as far as swapping the cables? It probably depends how careful you are with setting up your measurements. But again, getting back to the cable length differences, it really doesn't matter if this is measuring 2 inches away or 3 inches away. The instrument is going to compensate for that when you install the through adapter. And again, that's what this device is for here. So when is it important to use a phase match cable? And again, by phase matched, I mean that the length of the cable is the same when you're looking at the phase. So again, like if I had 2 pieces of cable like these 2 that came with the Nano, and let's say I put a pulse down both cables at exactly the same time, and I looked at where that pulse arrived at the end of the cable, what I'm saying is in time, it's going to arrive at exactly the same spot. And the way that you're normally going to do that is by adjusting or trimming the length of these cables to get them to match. So we call that phase matching. So what exactly do I mean by a full 2-port system? That's a system that's going to measure all 4 S parameters. So on the Nano again, we can source power out of channel 0, and we can look at the reflected power. So again, that's S11. On channel 1, I can look at the transmission power coming out of channel 0, and again, that's S21. So I would use this, for example, to look at the impedance of the device out here, where S21 is looking at the transmission, which essentially is going to be the gain or the loss of whatever device I have out here, for example, like an amplifier or an attenuator. What I can't do with the Nano is, for example, look at the reflected power coming off of channel 1, nor can I look at the power being returned back to channel 0. And so that is S22, and this is going to be S12. I'm assuming that there's quite a few people out there that are looking at this and saying, why would you ever do this? I can imagine that most of the people that are using the Nano are going to be amateur radio operators. So they're typically going to have some kind of a transceiver out here. There's my transceiver, and it's going to be connected to an antenna. So this has got some power amplifier in it, and that power is going to be going out to the antenna, and it's just going to be radiating off the antenna. And that's true to some degree. If you understand what SWR is, you know that essentially it's not a perfect world, and some of this energy that's being sent up to the antenna is going to be reflected back. So the power doesn't just go one direction, it goes both ways. So if I put a device between our transceiver and our antenna, I don't know what that is, but it could be a filter, maybe it's an SWR meter. It's something, you know. Our antenna has some impedance, and our amplifier has some impedance. You would like these two impedances to match, but what happens now is I've placed a device between the two, and so now I've got a case where, you know, I'm driving power through. Some of that's getting reflected back this direction, some of it's going on through to the antenna, some of it is coming back from the antenna trying to go into the device this direction. Because of the mismatch between the antenna and our device, some of that is getting reflected back to the antenna. So all four of these parameters are what's making up our 4S parameters. So in that third video that I made for the Nano, I was characterizing a crystal. One of the things I had mentioned in there was about a transfer relay, and essentially you can think of that as two switches back to back. So there's 4 ports on it. So in our case we could have like channel 0 and channel 1 go into our network analyzer, and then I could have a port A and a port B. So channel 0 can go to port A or port B, and channel 1 can go to B or A. So if channel 0 is going to A, channel 1 is going to B. And essentially what that's allowing us to do is to flip these two cables without disturbing our test setup. So if we have our NanoVNA, and this goes to our transfer relay, and then we have our 2 ports out here which go to whatever our dud is out here, we're now going to perform our sole calibration at this location here, not here. If I did a calibration, say on this cable here, and I switched to this one, and this cable is, you know, 3 inches longer, some other length, that's going to cause a pretty dramatic error in our measurement. So it becomes very important that these cables be matched in length. That same person again had asked about the overall length of the cable and if that was a problem. Of course you have losses of the cable, but another problem that you can run into is the network analyzer may not be able to handle different lengths of cable. So this is a reference plane extension cable accessory kit for my vintage HP network analyzer. What this is it's a kit full of all these various cables. Unfortunately the foam has deteriorated, but this is what these look like. You can see it's just a length of coax, semi-rigid, and these mount to the back of the S parameter test set. And you can see there's some that are quite a bit shorter. They're all different lengths. And what these are for is these compensate for the different length cables that you hook to the network analyzer. So if you remember in that first video where I showed the network analyzer, the actual cables that are attached are quite short. So for example, this is another set of cables, and these are quite a bit longer. These are made from an RG400, which is a mill standard coax. These are phase matched as well. Again, these are an APC7 connector on the end, and then on the other side we have an SMA connector. And each one of these is marked, so you can see 0 to 6 centimeters. So with this one being attached, you can have a cable on the output anywhere from 0 to 6 centimeters in length, and you could compensate for that then using the adjustments of the analyzer. Once you get beyond that, you can no longer compensate for it, and you have to add a new extension cable. Again, the upper end of this network analyzer is 2.6 gigahertz, and it's also a full 2-port system. So even though this network analyzer is quite old, it's still quite useful when compared to something like the Nano, which again is limited to 900 megahertz. So one of the things I thought about showing with this video was actually connecting this thing up to a transfer relay and using that to make some measurements. The problem that I have is most people are not going to be able to afford a good transfer relay. Typically those relays are very expensive. If you go to Pasternak's website, for example, they'll sell you a transfer relay. It'll typically cost you about $600 on up. You know, I imagine companies like Teledyne, they're probably going to charge you a fair amount more than that. I actually have an old transfer relay that I thought about using for this demo, but again, the problem is that's not something that people are typically going to be able to buy. Even if you could, you're probably going to buy it used off of eBay. That's not something I would normally recommend. If you do decide to buy a used one, I'd recommend that you hunt down the data sheets for it first, make sure it's going to fit your needs. But again, be aware that these transfer relays do wear out. It's very possible that it no longer meets the manufacturer's specifications. So I thought if I was going to show a transfer relay attached to this, I'd like to show something that was a little bit cheaper that people could probably afford. So I ended up making one. This is the first one that I made, and you can see it's quite small, fits in the palm of your hand. It's actually designed to butt right up against the Nano, just like this. So now our test cables would attach to these two connectors on the end like so, and we'd attach these up to our device under test. This particular one is using gas-ass switches from Macom. I didn't have a lot of luck with it. The problem with using these is it didn't really have good isolation between the two channels. So essentially what ends up happening is some of the signal that we're outputting on channel 0 actually directly gets coupled onto channel 1. It's bad enough with this particular relay that it basically wasn't usable. So this one was my first attempt, and it essentially was a bust. So I ended up trying to make a second one. That's this one here. This is using a RF relay from Omron. Again, the problem with this is the isolation rating for the relay. I was hoping when I looked at the data sheet that that was going to be very conservative, and it turns out essentially it's not. So I think the problem here is if you're going to try to make something like this and you're going to try to make it cheap, you probably can't do it and get real good performance. If you need that kind of isolation, you're probably going to end up having to pay for it. One way to get around that, for example, is to run multiple relays and physically keep them separate. But again, you're going to have to figure out a way to recombine those signals, and that's going to add error to the system. So yeah, I really don't have a good answer other than to buy an actual transfer relay. This one I think works good enough that we can actually use it to run some demonstrations today. I think before we do any of that, there's another test that I'd like to demonstrate, and essentially we're just going to be using a lot of coax cable here. If you go back and you look at that very first video that I made, you'd see that the calculations I made for the cable basically look like it's dead on. It came within an inch of what the actual length of the cable is. So there's a couple of things that I should mention about that. There's going to be a finite resolution for any vector network analyzer, including the Nano. So when I'm talking about resolution, I'm basically talking about the Nano's ability, or any network analyzer, to resolve this distance. So that's going to be a function of the frequency of the Nano. And this, again, the upper end is only going to be 900 megahertz. And there's some fairly good papers written on this subject that you could go out and read. But with the Nano, essentially it works out to a little over 5 inches is what I actually measure. The fact that it came up at 147, kind of a fluke. Essentially what I'm saying is I could take that and clip off an inch, and this thing couldn't even see that. And there's nothing really I can do with the Nano to improve that other than to increase the frequency. I've seen people post about possibly using even higher harmonics or changing something with the firmware where they think that they can get this thing running up higher than 900. Where I was actually thinking externally we could probably do this much simpler. You know, channel 0 again is our power output, And again, this can measure S11 or the reflected power on this. What I'm thinking is we would actually use channel 1 to measure the reflected power. So essentially you could think of these two ports being combined. So what we would do is take this output power, feed this into our mixer. So let's say this is going DC to 900 megahertz. Maybe out here I've got a gigahertz kind of signal and I'm sweeping between 1 gigahertz and 1900. So essentially now this becomes the output. So you may end up having to have an amplifier, some filtering and whatnot. But then on the back side we have our other port, and this goes into another mixer and then into channel 1. So this is taking our high frequency now and we're down converting that back to the frequency for the nano. So our reference oscillator drives both of these mixers, and what we may end up having to do is put some kind of a phase trimmer, on one leg of this to compensate for this. But you probably could make something like this work. Now, the reason I say that is I've done something similar to this with my old vintage HP analyzer, and I actually had ran some tests on that all the way up to 6 gigahertz. But I think that the problem that you'd have is trying to justify doing something like that with this $50 analyzer. Another problem was going to be the range. With the Nano, I can only collect 101 data points. And that works out, I think it was like maybe 250 inches is the total length of cable that I could measure with this thing. Maybe it's 200. It's going to be basically that 5 whatever inches times 101. Whatever that worked out to be, typically people are going to have to measure longer cables. And one of the things I had shown in the very last video was a crystal, and I was trying to model that crystal as part of an oscillator circuit inside a SPICE. And one of the things I showed was kind of how the network analyzer with its 100 samples basically sort of aliases. So if you're trying to show a Smith chart, for example, and you only have 101 data points and you're sweeping between 50 kilohertz and 900 megahertz, that's not a whole lot of data points per megahertz. And if you're looking at a crystal, essentially you don't see anything. What I did is essentially like a segmented sweep. I might sweep from 1 megahertz to 2, and then 2 to 3, and then 3 to 4. Each one of those segments will have 101 data points. And then when I'm all done collecting my sweep, I stitch all these back together and then I run my analysis on it. The reason I was doing this in that particular video was to try to improve the fidelity of the model that I was generating for SPICE. Another reason that you would want to do that is to increase your range of your TDR measurement. So I could actually, with the Nano, measure essentially any length of coax that I wanted just by increasing the number of sample points. I don't have to change the frequency at all. So if I doubled the number of sample points, essentially I'm going to double the length of coax that I'm going to be able to measure with that. So the plan today is to set up some demonstrations showing some of these techniques. So over the last couple of weeks I've also been running some other tests with this Nano. So for one of the tests, I'd taken this box that I made for a 32-bit A to D evaluation board from TI. This is basically an RF enclosure made out of circuit board material. All the joints are soldered on the inside, and then there's gasketing material up along the edge seam. So one of the things I did is I placed the Nano along with my transfer relay in a device that I was looking at all inside of this box. One of the problems that I run into is I've been having this thing sitting on the desk, basically located right next to me. So by placing the entire test setup inside of this RF enclosure, I remove a lot of the effects like from stray capacitance off of my body. So this actually improves some of my test results with the Nano. Let's just start. We'll look at our piece of coax cable here. This is the same piece that we tested before, and we'll just attach it to channel 0. Looking at the software again, we'll just drag our cursor over to the spike, and again you can see in the readout it's showing a 147.46 inches, and again that's very close to what our cable is at 147 inches. So what I'm claiming is that first of all, the range of the unit is limited by the number of sample points. So if I slide our cursor on over to the right, you can see our maximum range is 248 inches. That's all the length of the coax that I can measure with the Nano, unless I go to the segmented sampling. So what I'm going to do is go ahead and enable that. So I'll just turn off the auto sweep. We'll sweep again from 50 kilohertz up to 900 megahertz. But what I'm going to do is change our span to 100 megahertz. And now I'm going to go ahead and do our segmented sweep. Again, this is going to sweep starting off at 50 kilohertz up to 100 megahertz, and it's going to work its way on up to 900. You can see it's a lot more resolution now on the screen. You'll notice that the software has evolved quite a bit. It now supports a linear analog sweep. That's done in software. You can also see there's quite a few more options available. Okay, so now you can see it's collected 808 samples, and now let's drag our cursor to the right, and you can see we're now capable of measuring 2300 inches. And if we move the cursor again over to our peak, you can see it's still at 146 inches or so. Again, the resolution makes it a little difficult, so again, that's how you'd increase the range, is by adding more points. So this is a Sage phase trimmer. This is rated for DC up to 2 gigahertz. You can think of this as just a variable length piece of coax. What I'm going to do is insert this between our test cable and the Nano. And you can see that's moved our peak over to the right slightly. I'm not going to torque this for this demonstration. Let's just go ahead and move the cursor over. And you can see it's basically at 161 inches. Now what I'm going to do is adjust the phase trimmer, and let's see at what point we can see that peak step. Right there, you can see it's just starting to change, and there you have it. So let's move our cursor over now, and you can see it's 167 inches. So that is the resolution that we're able to detect with this. Again, I'm just adjusting it back. And again, we'll move our cursor back over, and we're back to 162 inches. So yeah, about 5 inches of resolution is all that we get with this setup. And again, to be clear, that's limited by the 900 megahertz. So one of the things that people use an instrument like this is to actually analyze circuit boards. And you could imagine that if you had some kind of a strip line or microstrip on a circuit board with various components, and you were going to try to track down where the actual problem was, if you only have a resolution of 5 inches, that's not really going to help you to solve those kinds of problems. You really need a network analyzer with a lot higher bandwidth than what this Nano has. So the way that we're calculating this length is we're essentially converting the frequency domain over to time domain, and we're doing that with an inverse FFT. But there's a lot more information that's available other than just the length of the cable. So let's talk a little bit about what a Beatty standard is. If you could imagine having a strip line on a circuit board, let's say this is on some Rogers or Arlon circuit board, and let's say this had a characteristic impedance of 50 ohms. So what I can do is actually use the network analyzer to measure that impedance. And what a Beatty standard does is it'll put some kind of a disturbance in that transmission line. So maybe they'll thicken it up or they'll thin it down. We can go then essentially from a 50 ohm to like a 25 ohm, and then back to a 50 ohm transmission line. And then these segments will have a calibrated length. And what we can do with the network analyzer then is actually measure the length and what the value of this is, so if it's 25 ohms or whatnot, and make sure that our calibration is correct. Again, the problem with this network analyzer is, a normal Beatty standard is only going to be a few inches long. We can't even detect anything down much below 5 inches. So to get any kind of resolution with this, we actually have to have a fairly long Beatty standard. So what we're going to do is we're going to take a piece of coax, and then we're going to attach this to a T, and we're going to attach 2 more pieces of coax together to 2 more T's, and then we're going to attach a resistor on the end here. So this will be 50 ohms, and essentially all these cable segments are going to be 50 ohms. These 2 sections of 50 ohm in parallel are going to provide me with a 25 ohm transmission line. So if we make these segments long enough, we could actually take these measurements with the Nano. So here's our Beatty standard. This is made up of 4 sections of coax, all of equal length. You can't see it right now because I've covered it up with tape. But there's a small circuit board where these 2 T's are formed. So what I'm going to do is go ahead and attach this up to our unit. Again, we'll just be attaching a terminator at the one end, and the other end we're just going to go ahead and connect to channel 0. Looking at the software, you can see it looks a little different. Let's go ahead and move the cursor over to the first peak, and we can see that this happens at somewhere around 24 inches. And then we see this other peak, and this happens at roughly 46 inches. So what's happening is I'm sending this signal down the unit, and again we're measuring the reflection. Eventually it hits this first T, and then some of that signal is reflected back. And then what happens is it continues to propagate down these two lengths of coax. Eventually it runs into the next T, and we see this second pulse. So you get one pulse for this guy and one pulse for this guy. And this is called the impulse mode. The other way to view this is with a step mode. And essentially what that's going to look like is something like this. So let me just bring that up. We do that by selecting Advanced and Time Domain. And now the left hand side of this screen is actually in impedance. So you can see we have this short length of coax, and it's about 20 some odd inches long. And then we have this length of 25 ohm coax, which is our two sections in parallel. And then it's basically 50 ohms. And again, that's because I have the end of the line here terminated. So let's go ahead and we'll remove our terminator. And what's going to happen is instead of being 50 ohms at the end, you're going to see that spike up. But you can see it recovers to 50 ohms. It stays there for quite a while. And then what happens is we get this big return spike, and that's because all the power that we've set down this length of coax is returning back to the network analyzer. And because it's an open, we're seeing it go positive. If we wanted to install a short, this is the short that came with the network analyzer. Let's just go ahead and apply that. The software is set up to assume that that first low peak is the 25 ohm standard. And you can see in the top center of the graph there's something called Beatty Reference. And what that does is it allows me to take a cable of a known impedance, assuming it's 25 ohms. That's pretty much an industry standard, and basically use that as a reference to measure other devices. So it doesn't have to be necessarily 25 ohms, it could be whatever, and it would be a relative measurement to this standard. So let's try this same test with a longer piece of coax. So again, I have these two lengths. These are each 147 inches long. You can see I have my two T's attached. At the common point of our far end, I have a 50 ohm terminator. It's not a very good terminator. And you can see I have another short length of coax here. We're going to be attaching that to channel 0. And this is what it looks like. So you can see now our software is displaying 146 inches. Again, what this is measuring is essentially the 50% point of this valley. It's measuring the width of this, and it's doing that in inches in this case. If I wanted to display this in impulse mode, again what we see is our two peaks. This first one is our first discontinuity caused by this T, and the second one again is caused by our output T. So you can see the total length of this cable looks like about 190 inches, and again that's including this segment of black cable. So hopefully that gives you a little bit more insight as far as what you can use the network analyzer for. It's not just to measure a length of a piece of coax or where it's failed. It can actually tell you what the impedance is at the failure point. So you can actually use a mode like this to, evaluate connectors or whatever. If you're interested in learning more about the vector network analyzer and how it does time domain measurements, there's several papers available out on the internet. I'd just fire up your favorite search engine and start reading. Somebody else had asked me what the input signal level was for the Nano. If I look at various test equipment that I have around the lab, you can see that a lot of this has different input ratings. Again, if we look at the Nano, there's two ports, and I think what they're asking is what's the input power that channel 1 can handle. And unfortunately, if you look in the user's manual, at least in the manuals I found, they never specify that. They do specify an output power. So whatever the output power of this is, obviously the analyzer has to be able to handle that as an input. So if you wanted to play it safe, you could just use that output level as your input level. You could pretty much guarantee that the unit's going to be linear in that region. But I'm afraid what this person's probably asking is, let's say we put an amplifier out here. We don't know what the gain of this is, but let's say we want to measure that. We're not going to do this with an amplifier. So instead what I'm going to do is take an RF generator, and I'm going to attach that to an attenuator, and I'm going to apply that to channel 1. And then what I'm going to do is set our VNA to run at a constant frequency, and I'll set this generator to that same frequency. We'll adjust it for a peak amplitude, and then what I'll do is adjust this attenuator, and we can measure where the signal starts to compress. And what I mean by that is, as I'm stepping that attenuator, we're expecting the network analyzer is basically going to track that. At some point, what's going to happen is the network analyzer is going to start to roll off, and once that happens, we know that we're operating in this nonlinear region. Normally, you're going to stay away from that. Of course, you know, there's many of these devices out there. This will be kind of a one-off measurement for this particular one, but it should give you some idea of where you could actually operate this thing if you did want to hook an amplifier to it. Currently I have this through attached to our network analyzer, and if we look at our software, I have a center frequency set for 20 megahertz, and I have the span set for 10 kilohertz. And looking at the display, you can see it's showing roughly 0 dB. The unit is calibrated. So what we'll do is disconnect our through. Now keep in mind that decibels is a dimensionless measurement. It's just a relative measurement. So when we say right now the display is 0 dB, we know that the Nano is putting out somewhere between -9 and -13.5 or something dB. So that is the actual absolute value. So typically for RF, that's going to be in dBW or dBm, which is going to be dB watts or dB milliwatts. So 0 dBm is 1 milliwatt, and 20 dBm would be 100 milliwatts. So here I have my step attenuator, and you can see now on our software we have a peak right in the center of the 20 megahertz, and you can see that peak is sitting right at -10 dB, and this is our RF generator. So now what we can do is adjust our attenuator up 10 dB, and we should see that peak go to 0. So let's just do that, and you can see it's -0.009015, so pretty much at 0. Let's go ahead and we'll go up one more step, 9.73. So it started to compress. Let's go ahead and we'll take it back to 0. And now what we're going to do is step by 1 dB increments. So this will be 1 dB. You can see it's dead on. Here's 2. Here's 3. 4. 5. 6, 7, right there, it's starting to compress. We could just increase this and see where we're off by a margin of 1 dB. We adjusted the step attenuator back to 0, and now we're going to take another 10 dB off. Again, this should be reading roughly 10 dB plus. So let's go ahead and increase this a little further. It should be 11, 12, 13, right about here. This should be 14 dB, and you can see it's reading 13. So this would be our 1 dB compression point for the network analyzer. So if we wanted to know the absolute value, I currently have the Marconi set for 7.3 dBm output. The attenuator right now is set for 6 dB of attenuation. So the signal that's actually being supplied to the network analyzer is going to be 1.3 dBm. So I think it's safe to say we can use this thing pretty much at 0 dBm or 1 milliwatt. I think beyond that you're going to start to see some compression errors. Also, I guess while I have this out here, this is a piece of semi-rigid coax. That connector alone probably costs as much as the Nano. Of course, you don't need cables like this if you're working with the Nano. Again, what I have here are 2 homemade transfer relays. Again, the one on the left is using gallium arsenide technology, while the one on the right is using a mechanical relay from Omron. This relay, I think it's a G6K RF series. It is a non-latching type relay. The cost on this in singles I think was about $20. Again, the performance of the relay is not very good, but again, my goal for making these prototypes was to try to come up with a low-cost way to actually make a transfer relay, something that was readily available that people could probably afford if they were buying the Nano. To drive this thing, all I have here is an FTDI TTL cable. I'm using one of the handshake signals in this case, and the 5 volts off of the USB to power this. So this cable just plugs into one of the PC's USB ports, and we can go ahead then and attach this to the Nano like so. Again, you want to cinch these down evenly. So I've received several questions about these calibration standards. One of the common questions is if I sell them. I don't. Another question is if I release the artwork. And again, I don't do that. I didn't create this channel to sell products. Basically, the only thing I do on this channel is distribute information. Again, that's for free. I never ask for any handouts. I have no Patreon account. This is purely my way of giving back to the community. So I'm sure people are going to ask about this transfer relay, if I'm going to offer this as a sellable product, and I have no intention on doing that. Again, for one thing, the performance isn't very good, but if somebody wanted to produce a low-cost transfer relay, you know, it's not going to break my heart if they steal this design and start producing it. Again, what we need to do is go ahead and torque this. And then we'll just attach our two cables to the transfer relay, and again we'll go ahead and torque these. And we'll go ahead and reattach our PC's USB port to the Nano. So the first thing that we need to do is calibrate this system. Unfortunately, the problem with showing you how that's done is the software that comes with Microsoft Windows 10 to do frame captures can't seem to grab dialog boxes. So what I'm going to do is point the camera at the screen. It's going to be a little rough, but I'll walk you through the menus on how the calibration is performed. Both of these channels need to be calibrated, so we actually have to apply a short open load on each one of these ports. And then what we have to do is apply a through, and then with all those measurements we can compensate for the errors of this system. So I'm going to go ahead and move the camera. Alright, again, this is looking at our software. What I'm going to do is just select link, and we'll enable the auto sweep. What I'm going to do again is just attach our load to port A, and you can see what this kind of looks like. Let's go ahead and we'll store that. Let me go ahead and we'll move our calibration standard to port B, and let's change our transfer relay. I can do that manually with the software. That's done by selecting channel 0-A, and look at the difference between these two waveforms. Let me see if I can zoom in a little closer with the camera. See how much error there is between these two? So if I were to compensate just one channel, there's still going to be quite a bit of error between these two. And that's the reason that we have to run a full 2-port calibration with this transfer relay. And that's going to be true for any transfer relay if you're trying to get optimum measurements. What we do normally is I run this 2-port cal. You see it comes up with this menu, and it's basically asking me, do I want to run a new calibration, or I can load an old calibration, or I can use one of the Nano's internal calibrations. And the internal calibration that you'd want to select is done by this widget right here where it says internal cal. So currently that's going to load up the internal calibration 0 of the Nano if I select internal. So let's just do a new calibration. We won't actually go through this, but you can see it saying install a short. It does a sweep, and then it says install an open on port A. And then it wants to install a load on port A. You can hear it just change the state of the transfer relay, and now we want to install the short on port B, and an open on port B, and a load on port B. Then we go ahead and install the through, and now the software is asking me where I want to store this calibration. So this is actually going to create a file. In this case it's called calibration.cal. I select OK, and here's our calibration. Obviously this one is not very good, so let's go ahead and we'll load one of the previous calibrations. So we select 2-port cal, press old. So I'm going to select this file here. This is starting off at 10 megahertz and it's sweeping up to 50 megahertz. So let me try to zoom into the Smith chart a little bit for you. Okay, so currently nothing is attached to the 2 ports of the network analyzer, and you can see there's just a slight stub right here, and this is because we don't have the open installed. So let's go ahead and do that, and currently port A is selected, so, and now you can see there's a dot right on the open. Let's go ahead and apply the load. So again, this is 50 ohms, and you can see our dot right smack in the center of the screen. And again, let's apply our short, and again we're going to see a dot on the far left of the screen. So let's go ahead and we'll change the transfer relay. So this is going to be using port B now. Again, our short is attached to port A. Let's just move that over to port B. And of course, we get a dot on the far left with it connected to port B. Same thing if I attach our load, we'll see a dot smack in the center with port B selected. There you have it. And of course, the same is going to be true with the open attached. So let's go to transmission, and you can kind of see the problem right now. So at 10 megahertz, it's down about 40 dB. But as we work our way up to 50 megahertz, we're clear up at almost 30 dB. And that's what I was saying. If you really want a good relay, you're going to have to pay for it. So anyway, with our through attached, you can see we're basically flat with phase and gain. So there's another sanity check that we can perform that's fairly well known. It's called the T-check. There's a paper that's been published by Rohde Schwarz that explains that. You can look that up. Or I linked it in the eevblog forums. But essentially all that test is it's a T with a 50 ohm terminator attached to the center of it. And then the two ports of the network analyzer attached to the two ends of the T. And then you can perform a cross correlation using all four S parameters, and then basically mathematically you can validate how well the instrument is actually calibrated. So if you take the time to read that paper, the output of the display is going to be in a percentage. They'll show it as 100% as being a good instrument, and any deviation from that 100% is basically an error. If you get up around 10% or so, that's probably okay. 15% gets a little marginal. At 20%, you basically throw out the calibration. So again, the instrument is calibrated to these small test boards, and the T is also built up on this test board. You can see we have two 1206 100 ohm resistors in parallel. We can go ahead and attach this between our two ports. And now what we can do on our software is select two-port T-check, or we can just select the T-check button. So when I do that, it's going to change the analyzer over to T-check. It's asking us to install the 50 ohm T-check adapter, which we've already done. We select OK. So this is looking at the data we just collected. Again, this is a full two-port measurement, so we're measuring all four S parameters in this case. So you can see we start off at 10 megahertz at 108%, and at 50 megahertz we get down to 93.3. So again, roughly plus or minus 8% of error. So that's definitely usable. Let's go ahead and we'll load up a second calibration. So again, I just select port 2 cal, and we select old. And this time we're going to select the 1 to 500 megahertz. So you can see we start off at roughly 25 ohms. Let's go ahead and change the state of the transfer relay. You can see it's slightly different between the two, and of course that's after performing the calibration. Let's go ahead and again we'll select the T-check. So you can see between 1 and 500 megahertz, it's between plus or minus 20% still. So I'd say it's marginally usable, even all the way up to 500 megahertz. You start getting beyond that, things fall apart pretty quick. Let's just go ahead and we'll reload our 1 to 50 megahertz cal. You can see it's finished, so we again are scaled between 10 and 50 megahertz. And let's repeat our T-check. And there you go, between 108 and 92.7. So again, we're back into a fairly usable area. So getting back to amplifiers, all I have here is a small RF transistor. I'm going to be attaching this to our transfer relay, and we can try to make some measurements with this. Of course, this transistor isn't going to do a whole lot unless we apply some kind of bias current. And if you look at our box, there's two additional connectors that I haven't talked about, and these are marked bias. This box actually includes two bias tees. If you don't know what a bias tee is, I have a DC block coming from the transfer relay up to the port, and then I have a DC connection between this bias port and the port. We also want to block the RF coming from port B back to the bias. The way we do that is we have an inductor in here and some capacitors that form a filter, so they allow the DC to pass into port B, and that's the same for both port A and port B. So there's two separate bias tees. So for the drive side, we're going to attach this device. This is a DC block. Again, this is produced by Mini Circuits. So this will be on the base of the transistor, and again we can attach this to port A. Alright, we can just go ahead and snug all these down. Basically, we don't want any of this moving. Now what we need to do is apply power to this. So we'll attach this to the bias T for port B. And again, this just goes back to a small bench power supply. You can see the dot here in the center, and again, that's because we're using the software's built-in calibration, not the nanos. So looking at our software, you can see we're still at -14, -15 dB or so. Let's go ahead and we'll start increasing the current through the collector. And you can see we're almost starting to generate some gain out of it. Let's turn it up a little bit higher. There you go. You can see now we have about 4 dB of gain. So our transistor actually is amplifying right now. So let's say we wanted to measure the 1 dB compression point for this particular setup. You can see what I've done is I've attached our step attenuator to the drive side of our transistor. Currently this is set for -10 dB. You can see the nano is displaying roughly 7.8 or so dB. So let's go ahead and increment this by 1 dB steps. So here's 1 dB. Here's 2. Looks good so far. Here's 3. And right there, you can see it's already starting to compress. Here's 4. Yep, it's getting worse. We're definitely in the non-linear range of the unit. This is well beyond the 1 dB compression point right here. Let's say you wanted to measure a much larger amplifier, you know, something in the several watts. That certainly could be done. Of course, if you don't know what you're doing, you could risk damaging the unit, but then again, you're only going to be out $50, so not that big of a deal. And again, the way you normally do that is by connecting some attenuators to the output of the amplifier. Just to give you an idea what some of these look like, you can see the one on the right. This is a power attenuator, fairly good size. If you're looking at larger amplifiers, you're probably looking at something like this. This is a 50 ohm load with a tap. I think I characterized this all the way beyond 100 megahertz. And you know, of course you could series these up, so we could take a large attenuator like this, attach it to our tap load, and again, the attenuation that's off of this tap should allow me to directly connect right to the nano. I've done measurements like that with my oscilloscopes actually. Okay, I'm sure this video is starting to get quite long, but there's one last thing I'd like to show you. In the last video I made for the nano, I was showing how to use the nano to collect some data to drive a SPICE engine or create SPICE models using a touchstone file. And I basically did that for a crystal and a resistor of all things. And the touchstone files I created were only for S11. So essentially I was using the crystal in shunt mode instead of in series. What I have here is a small low pass filter that I put together. This is a 12 megahertz low pass 5-pole filter. It's a 50 ohm-ish, somewhere around there. And what I'm going to do is show you how a full 2-port analysis could be ran on this. So if we look at our software, basically what I'm going to do is load in a different calibration. So again, we select 2-port cal, we select old, and I'm going to select the 50 kilohertz to 20 megahertz file. Okay, and our calibration is now loaded up. So let's go ahead and change the transfer relay. So you can see there is some difference between the two. Again, let me just save this as a reference, and let's change the relay back to the other state. So you can see there is a slight difference between the two ports. Again, this is after a full 2-port calibration. So now let's say I wanted to run a 2-port sweep. We do that by selecting the 2-port sweep button. Let's go ahead and do that. We can go to advanced, and this is displaying all 4 S parameters plus the SWR. It also displays S11 and S12 in Smith charts. What I could do with this information now is go back to the main menu, and you can see I've added a new button called S2P Save. So that'll generate a 2-port touchstone file. I can just select that and we give it the default name, and that would generate our file. And again, that touchstone file would include all 4 S parameters. and then from there we could feed that into our Spice engine and we could actually simulate this filter on there. Let's go ahead and we'll select transmission. You can see this is what the filter looks like. We can also look at the reflection coefficient. Well, I think that's going to be it for this video. My one and only Patreon flipper had actually asked a question as well, and unfortunately I can't really show him what he was asking. So if any of you other viewers have technical questions about the things that I've shown in any of these videos, feel free to ask. I'm not opposed to doing another question and answer video. Hopefully this has helped clear up a lot of what I had shown previously. So until the next video, later.